So inside a laboratory right now, there are scientists trying to build a machine using, well, basically a single grain of sand.
Yeah.
And they are cooling that grain of sand to a temperature that is actually colder than the deepest void of outer space.
Which is, hard to even wrap your head around.
Right. And they are doing this because they want to isolate a single electron, literally flip it upside down and use it to calculate problems that would take your current laptop, literally 1 million years to solve.
Oh, at least 1 million. Easily.
But okay, here is the craziest part for you listening. The biggest competitor to that multi-billion-dollar hyper-frozen grain of sand might just be the eye of a migratory bird.
Yeah. It is, it's the ultimate collision of high-energy physics, massive industrial engineering, and then, strangely enough, evolutionary biology.
It's wild.
It really is. We are looking at a landscape right now where the fundamental rules of how we process information are just being completely rewritten.
Well, welcome to this deep dive. If you've been following the tech world lately, you know the buzzwords, right? You hear them everywhere. But today, we are going to actually understand what they mean.
Exactly. We're cutting through the jargon.
Yeah. We are looking at the state of quantum computing right now in the year 2026. Specifically, we are exploring this wild array of QuID technologies.
These microscopic engines of quantum calculation.
Right. And they are fighting a brutal, high-stakes war to become the global standard. So our mission today is to give you a really clear, comprehensive understanding of how these different technologies actually work underneath the hood.
Which is fascinating, by the way.
Oh, totally. We're going to talk about who is winning the commercial race right now, and we're going to explore some genuinely mind-bending, non-conventional approaches that are just starting to emerge.
And, the reason you should care about this right now, the reason 2025 and 2026 are going to be the years historians point back to, is that we are witnessing a fundamental irreversible shift.
Like a turning point.
Exactly. Because for decades, quantum computing was essentially a chalkboard exercise. It was pure scientific demonstration.
Right, like, hey, look, we did it once.
Yeah, exactly. The goal was just to prove a single quantum bit, a qubit, could exist without just instantly collapsing.
Yeah.
Now,
we
have officially moved into the era of engineering scalability and fault tolerance. We are in what industry analysts are calling a multiple competing architectures phase.
Which honestly reminds me of the chaotic early days of classical computing.
Oh, absolutely.
Back when people were screaming at each other at conferences over whether the future belonged to, vacuum tubes or mechanical relays or these weird new things called solid-state transistors.
That is the perfect historical parallel.
Yeah.
Because no single architecture has won yet.
Yeah.
And the stakes could not be higher.
Yeah.
The architecture that wins this race isn't just going to define the next generation of computers. It's going to define the next century of material science, pharmaceutical discovery, global logistics, everything.
It changes everything.
Right. If you can perfectly simulate a molecule, you don't need 20 years of trial and error to find a cure for Alzheimer's. You can just simulate the cure in an afternoon. That is what is actually on the line here.
Okay, so let's get into it. If we want to understand this race, we have to look at the different horses on the track.
Right.
I want to start with the giants, the industrial heavyweights that really kind of forced this entire industry into existence.
The household names.
Yeah, exactly. If you've ever seen a picture of a quantum computer in an article or a magazine, you know exactly what I'm talking about. It looks like a beautiful, terrifying golden chandelier hanging inside this giant metal cylinder.
It does. It's an iconic visual.
It really is. And that is a superconducting quantum computer.
But, the funny thing is, that golden chandelier isn't actually the computer itself.
Right.
That is just the refrigerator.
Yeah, the computer itself is just a tiny little chip sitting at the very, very bottom of that chandelier. So let's unpack how this actually works. Superconducting qubits use what are essentially artificial atoms, right?
Yes. They don't use real atoms from the periodic table. They build tiny electrical circuits on a chip that behaves like a semiconductor.
Okay.
And the critical component there is something called a Josephson junction. But to make this circuit behave quantum mechanically, they have to plunge it into an environment of just extreme cold. Yeah. We're talking 10 to 20 millikelvin.
Which is, how cold is that really?
Well, to give you a sense of scale, absolute zero is the temperature where all atomic motion completely stops. Deep space, like the void between galaxies, is roughly 2.7 Kelvin because it's warmed slightly by the cosmic microwave background radiation left over from the Big Bang.
Right.
20 millikelvin is a tiny fraction of a single degree above absolute zero. It is significantly colder than the natural universe.
That is just insane to think about. And to get there, they use these massive machines called dilution refrigerator.
Yes, the golden chandeliers.
Right. And they use a mix of specialized helium isotopes, continuously pumping them in this really complex cycle to just drag the heat out of the system. I read it takes days just to cool the thing down before you can even turn it on.
Oh yeah, it's a massive process.
But let's talk about that Josephson junction you mentioned. What exactly is happening down there at 20 millikelvin that turns a normal circuit into a quantum machine?
So a Josephson junction is brilliantly simple in its construction, but profound in its physics. It is essentially two superconducting metals separated by an impossibly thin layer of an insulator.
Like, how thin are we talking?
Usually aluminum oxide, maybe a nanometer thick, just incredibly thin.
Wow.
Now, at room temperature, this is just a broken circuit. Electricity hits the insulator and stops.
Right, because it's an insulator. It blocks the current.
Exactly. But when you drop the temperature to near absolute zero, the metals become superconducting. They lose all electrical resistance. Yeah. And the electrons inside the metal, they pair up into what are called Cooper pairs.
Okay, Cooper pairs. Why do they matter?
Because when electrons pair up like this, they stop behaving like individual bouncing particles, and they start behaving like a unified quantum wave.
Oh, interesting.
And because they act like a wave, they can do something impossible in classical physics. They can tunnel.
Tunnel, like through the insulator?
Yes. Even though there is a solid physical wall of insulation blocking their path, the quantum wave function of the Cooper pair extends through the wall. They essentially teleport from one side of the insulator to the other.
Teleporting through a solid wall, that's magic.
It's quantum tunneling, and that tunneling effect creates a very specific, nonlinear energy landscape. It allows researchers to isolate two distinct energy levels and say, okay, this bottom level is our 0, and this top level is our 1.
Got it.
And because it's a quantum system, we can pulse it with perfectly timed microwaves to put it into a superposition of both 0 and 1 simultaneously.
Okay, but here is where I struggle with this approach. My understanding is that maintaining that superposition in a superconducting circuit is like trying to keep a spinning top perfectly balanced on the tip of a needle.
That's a good analogy.
If a single molecule of wind hits it, it falls over. In this case, if a stray microwave photon from the room, or I don't know, a tiny vibration from a passing truck outside, or a microscopic temperature bump hits that chip, the top falls over. The quantum state collapses.
Right. We call that decoherence.
Decoherence. So my question to you is, if they are so incredibly fragile and they require millions of dollars of extreme helium cooling infrastructure just to run a single calculation, why is this the leading approach?
It's a fair question.
Why are the biggest tech companies on Earth betting everything on this?
Well, it comes down to a very pragmatic engineering trade-off. You are absolutely right that their coherence times, the lifespan of the qubit, are terrible. The superconducting qubit typically loses its quantum state in microseconds. It dies incredibly fast.
It's just a flash.
Yeah. However, their gate speeds, which is the actual time it takes to fire a microwave pulse and perform a calculation on that qubit, are blistering fast. We are talking nanoseconds.
Okay, so it dies fast, but it thinks faster.
Exactly.
Yeah.
You can cram a massive number of operations into that tiny microsecond window. But the real reason, the industrial advantage that makes the giants love this approach, is the manufacturing.
Making them.
Right. We already know how to print electrical circuits. We can use the existing semiconductor lithography infrastructure. You don't have to invent a completely new way of manufacturing from scratch.
That makes total sense.
Yeah, we can take the factories we spent the last 50 years perfecting for classical computer chips and just adapt them to print these artificial atoms.
Which explains why the companies dominating this space are the ones with massive hardware experience. Look at IBM right now in 2026. They are charging ahead with their Heron processor family.
They've made huge strides.
Yeah, and what's fascinating is they aren't just isolating these machines in a lab anymore. In early 2026, IBM actually linked up a Heron processor with Japan's Fugaku supercomputer.
That is a critical milestone because it proves hybrid computing. They're using the classical supercomputer to handle the heavy lifting of the routine data processing, and then they're handing off the impossibly complex quantum mechanical calculations, in this case it was complex molecular simulations, to the golden chandelier.
Right. And IBM's roadmap is aggressive. They are targeting a system called QuEra by 2029, which is aiming for over 4,000 qubits connected via quantum communication links.
Which is huge.
But I want to pivot to Google, because Google Quantum AI just hit a milestone with a chip called Willow that completely blew my mind. Help me understand this, because it feels like it reverses a fundamental law of physics.
Oh, you're referring to their error correction milestone. And yes, it is arguably more important than their initial quantum supremacy claim from a few years ago.
Really?
Well, let's frame why this is so profound. In classical computing, if you want a more powerful computer, what do? You just add more transistors to the chip.
Right. More parts equals more power.
But in quantum computing, because of that extreme fragility you mentioned earlier, the spinning top on the needle, adding more physical qubits actually adds more noise.
Oh, I see.
Every new wire you connect, every new qubit you place on the chip is another pathway for heat and interference to sneak in. So historically, the larger you made the quantum computer, the worse it performed. The errors overwhelmed the calculations.
That sounds like a complete dead end for the whole industry. Like, how do you fix that?
It was the looming nightmare. But Google's Willow chip, which is 105 qubits, proved that if you use very specific, highly complex error correction codes, essentially spreading the information of one logical data point across a grid of many physical qubits, the errors actually decrease exponentially as you make the system larger.
Wait, hang on. That violates everything I know about mechanical engineering. If I add 100 noisy, squeaky gears to a clock, the clock doesn't suddenly become more accurate. How does adding noisy qubits make the system quieter?
It's because of the surface code error correction. Imagine a choir where every singer occasionally sings the wrong note.
Okay.
If you only have 3 singers, a wrong note ruins the chord. But if you have 1,000 singers and they are constantly listening to their immediate neighbors and adjusting their pitch to match the consensus, a few wrong notes are instantly absorbed and corrected by the collective.
Oh, wow.
Google proved that they finally crossed the threshold where the collective correction outpaces the individual noise. Scaling up finally makes the system more stable.
That is massive. And it's not just Google and IBM doing this. You've got Rigetti Computing hitting over 99% fidelity on their Anka 3 chip. You have IQM in Europe literally dropping on-premises quantum computers into high-performance computing centers like Oak Ridge National Laboratory.
It's moving fast.
Superconducting is the heavy industry of the quantum world. But it is not the only way.
Far from it.
Which brings us to the next massive contender, trapped ion qubits. If superconducting is about building artificial atoms on a circuit board, trapped ions are about looking at nature and saying, you know what, nature already built a perfect atom, let's just use that.
Exactly. It is the purist's approach to quantum computing.
So instead of a printed circuit, they take actual individual atoms, ions like deuterium or barium, and because these atoms are ions, meaning they have an electrical charge, researchers can suspend them in a complete vacuum using invisible electromagnetic fields.
They just trap them in midair.
Yeah. Then, instead of firing microwave pulses at a chip, they zap these floating atoms with highly precise lasers to encode and manipulate the quantum information.
And what is truly beautiful about this approach is the absolute perfection of the qubit itself.
Because it's natural.
Right. Every single atom of deuterium in the universe is exactly, completely identical to every other atom of deuterium. There are no manufacturing defects. You don't have to worry about a microscopic smudge on your lithography mask ruining the chip, which is a constant headache for the superconducting folks.
I bet.
And because these atoms are floating in a vacuum, physically isolated from any solid surface, their coherence times are stunning. While a superconducting qubit dies in microseconds, a trapped ion can hold its quantum state for seconds or even minutes.
Oh, wait, but I'm going to push back here. When I picture this, I picture someone trying to juggle 30 bowling pins while balancing on a unicycle, using nothing but precise laser pointers to keep the pins in the air.
That's a stressful image.
Right, yes, the pins are perfectly identical, but the laser control system sounds like an absolute nightmare. If you're individually laser targeting atoms floating in a vacuum, how can you possibly scale that up? We need millions of qubits to run real-world pharmaceutical simulations. You can't just have a million individual laser beams crisscrossing inside a tiny vacuum chamber. The optics alone would be impossible to align.
You have hit on the exact bottleneck that has haunted trapped ion researchers for a decade. The atoms are perfect, but the classical control hardware required to fire those lasers is gargantuan.
I mean, it must be huge.
You end up with a vacuum chamber the size of a shoebox, surrounded by a room the size of a gymnasium filled with perfectly aligned mirrors, lenses, and laser modulators. The slightest vibration in the floor misaligns a laser, and you hit the wrong atom.
So how are they surviving in the market right now? How is this a real business?
Because of a massive pivot that is playing out right now in 2026. Look at IonQ. They are a publicly traded leader in this space. In late 2025, they made a $1.8 billion acquisition of a company called Oxford Ionics. And the technology Oxford Ionics developed is called electronic qubit control, or EQC.
Okay, break down EQC for me. What does it do?
EQC essentially throws the laser pointers in the trash.
Really?
At least for the calculation phase. Instead of firing massive external lasers through windows into the vacuum chamber to manipulate the ions, they use electronic signals. They place a standard silicon microchip directly underneath the floating atoms.
Oh, interesting.
Yeah, and by running perfectly timed microscopic currents through the wires on that chip, they generate highly localized, highly precise magnetic fields. Those magnetic fields reach up and perform the quantum gates on the atoms directly.
Wait, so the atoms are still floating in the vacuum, but they're being controlled by magnetic fields generated by a chip just millimeters away.
Exactly. They still use lasers initially to cool the atoms down and at the end to read the final results, but the actual dynamic computation is driven electronically. This solves the scalability problem almost overnight. Suddenly, you don't need a gymnasium full of optics. You can pack thousands of ions into an array above a silicon chip and control them with the same kind of electronic routing we use in normal computers.
That is brilliant. You get the perfection of the natural atom, but the scalable control of a silicon chip.
Yeah.
And IonQ isn't alone in pushing this field forward. You have Quantinuum, which is hitting major milestones with real-time fault tolerance. You have Alpine Quantum Technologies building these sleek, rack-mounted trapped ion systems that just slide right into standard data center servers.
Right. So if you were looking at these first two heavyweights, the dichotomy is clear. If you want raw speed and you want to leverage 50 years of established microchip manufacturing, you go superconducting. If you want pristine accuracy, incredibly high fidelity, and long memory times, you go trapped ion.
Okay, so that's the old guard, the heavyweights. But here is where the landscape starts getting really disruptive. We are moving into the technologies that are scaling at terrifying speeds. Let's talk about neutral atoms and silicon spin qubits.
This is where we see researchers trying to find the ultimate middle ground.
Right, so trapped ions give us perfection, but holding charged particles in electromagnetic fields is tricky because they naturally want to repel each other. Is there a way to get that atomic perfection without the electromagnetic juggling act?
And there is.
Enter neutral atoms. Instead of charged ions, these systems use uncharged atoms, things like rubidium or strontium.
And because they have no electrical charge, an electromagnetic field won't hold them. They would just float away.
Exactly. So how do they trap them? They use something called optical tweezers, which honestly sounds like science fiction. They're essentially highly focused laser beams inside a vacuum chamber.
The physics of an optical tweezer is fascinating. Light actually exerts physical pressure. It has a momentum.
Right.
So by focusing a laser beam tightly through a microscopic lens, you create a gradient of light intensity. The neutral atom gets pulled toward the absolute brightest center of the beam and gets stuck there, literally suspended in light.
It's a microscopic tractor beam.
It is.
Imagine a wall of 1,000 microscopic tractor beams, each holding a single, identical marble perfectly still in a 2D or 3D grid. But here's my fundamental question. If these atoms don't have an electrical charge, they don't naturally interact with each other. If I put two neutral atoms next to each other, they just ignore each other.
Correct.
So if they can't feel each other, how do you get them to perform a calculation together? How do they talk?
This is where we use a beautiful quirk of quantum physics called Rydberg states. When the researchers want two of these neutral atoms to interact and perform a logic gate, they hit them with a very specific, ultra-fast pulse of a different laser.
Okay.
This laser injects exact energy into the atom, exciting its outermost electron.
What happens to the electron?
It jumps into a massive orbit. The electron cloud literally puffs out to an enormous size, well, relative to the atom, of course. We call this a Rydberg atom.
Oh, wow.
When it puffs out, the atom suddenly develops a strong dipole moment. It becomes highly sensitive to the electrical environment around it. Suddenly, it can feel its neighbor. The puffed up atoms interact. They entangle, the quantum gate is performed, and then the researchers immediately hit it with another laser to de-excite them.
They shrink back down.
They shrink back down, the interaction turns off, and they go back to ignoring each other. It is an incredibly clean way to control entanglement. You only turn on the interaction exactly when you need it.
Puffing up to talk, shrinking down to isolate, that is so elegant. And the scalability seems unparalleled. Because optical tweezers are just projected patterns of light, You aren't physically wiring anything. You can pack thousands of these atoms into a grid. But the craziest part I read is that they can physically move the atoms around during the computation.
Yes, dynamic reconfiguration. In a superconducting chip, qubit A is permanently wired to qubit B. They can never talk to qubit Z all the way across the chip.
Right, they're stuck.
But in a neutral atom system, you can just steer the optical tweezer. You can pick up atom A, drag it across the array to entangle it with atom Z, and then move it back.
The 2026 real-world milestones for neutral atoms are just jaw-dropping. Let's look at QuEra computing. They spun out of research from Harvard and MIT. In early 2026, they published a paper demonstrating 96 verified logical qubits out of an array of just 448 physical atoms.
We need to underline how huge that is.
Yeah.
We talked about Google's surface code error correction earlier, where you need maybe 1,000 physical qubits just to create one reliable, error-free logical qubit.
Yeah, massive overhead.
QuEra managed to get 96 logical qubits out of just 448 physical ones. It proves that the error correction overhead for neutral atoms is drastically lower. The atoms are so natural and the dynamic movement is so efficient that they don't need millions of physical qubits to do useful work.
And then there is atom computing. They just hit a milestone of over 1,000 qubits. But the part that made me stop reading and reread the paragraph is their coherence time. They are using the nuclear spin states of strontium atoms rather than the electron spin.
Yep.
And because the nucleus is so deeply buried and protected within the atom, they achieved a coherence time of 40 seconds.
30 seconds.
40 seconds. We just spent 10 minutes talking about superconducting qubits dying in a few microseconds. 40 seconds is an absolute eternity in quantum mechanics.
It really is.
But let me challenge that. 40 seconds is a long time, sure, but it's still less than a minute. If I want to run a complex logistics optimization that takes an hour to compute, how does a 40-second memory help me? Does the whole computer just wipe itself every minute?
It's a great question.
Yeah.
You don't run the computation continuously for an hour without checks. Use error correction. If the raw physical qubit can survive for 40 seconds on its own, it gives the error correction algorithms an eternity to measure the surrounding environment, detect any incoming noise, and apply correcting pulses before the state is lost.
Oh, I get it.
Yeah, a long baseline coherence time makes error correction infinitely easier to engineer. You aren't constantly fighting a microsecond clock.
That makes sense. It gives the software room to breathe. Okay, let's pivot to the other rapid scalar in this segment, silicon spin qubits, also known as quantum dots. This is a very different philosophy. We are leaving the floating lasers behind.
Totally different.
The core idea here is trapping the spin of a single electron inside a nanoscale dot of silicon.
It is the ultimate evolution of miniaturization.
My analogy here is that building a silicon spin qubit is like walking onto a massive, miles-long sandy beach, finding one single specific grain of sand and flipping it upside down to write a piece of data.
That's practically what it is.
But my pushback to this entire modality is this. Aren't we just using silicon? You're talking about printing circuits on silicon wafers. Isn't this basically exactly what we do with classical computer chips? Intel and TSMC already do this all day long.
Yes. That isn't a bug, that is the entire value proposition.
Really?
Think about it. Every other technology we've discussed, from the extreme dilution refrigerators to the optical tweezer arrays, requires bespoke, highly specialized custom manufacturing. Silicon spin qubits are explicitly designed to leverage the existing global CMOS foundry infrastructure.
Define CMOS for the audience.
CMOS stands for Complementary Metal Oxide Semiconductor. It is the underlying fabrication technology used to make the chips in your laptop, your smartphone, your car. It is essentially the greatest, most precise printing press humanity has ever invented.
Right.
We use photolithography, using light to etch microscopic patterns into silicon to put billions of transistors onto a single chip. The silicon spin approach says, if we can engineer a quantum dot using that exact same photolithography process, we can print millions of qubits on a single wafer for pennies.
Ah, so it's a brute force manufacturing play. You don't have to build new factories. You just send a different blueprint to the factories that already exist.
Precisely. Now, they still require cryogenic cooling. You still need to drop them down to about 1 Kelvin to isolate the electron spin from thermal noise.
Wait, 1 Kelvin? The superconducting ones needed 15 millikelvin. Is 1 Kelvin really that much of a difference?
The engineering difference is night and day. Achieving 15 millikelvin requires those massive multi-million-dollar helium dilution setups. Achieving 1 Kelvin is relatively straightforward cryogenic engineering.
Really?
Yeah, and furthermore, at 1 Kelvin, you have enough cooling power left over to put the classical control electronics, the signal routers and amplifiers, inside the fridge right next to the quantum chip.
Oh, that's huge.
Right, because with superconducting at 15 millikelvin, any controlled electronics would generate too much heat, so they have to sit far away, outside the fridge, which creates latency and wiring nightmares.
So the 2026 updates show the silicon dream is finally becoming reality. Look at an Australian company called Dirac. They had a breakthrough publishing over 99% fidelity on silicon qubits that were manufactured using standard 300mm CMOS processes.
This was a massive indication. For years, physicists argued that commercial silicon foundries were too dirty. They said the microscopic imperfections in mass-produced silicon would ruin the delicate quantum states.
But they didn't.
Dirac proved them wrong. They proved that foundry-made, mass-produced qubits are actually viable for high-fidelity calculations.
And obviously, the classical chip giants are circling this. Intel is mass-producing their Tunnel Falls silicon spin chips right on their own commercial fabrication lines. You have Quantum Motion out of UK doing brilliant work. If Silicon Spin manages to master the control electronics, they might just outscale everyone else simply because the trillion-dollar global supply chain already exists.
It's a phenomenal gamble.
Okay, so up to this point, every single technology we've talked about, superconducting, trapped ions, neutral atoms, silicon spin, they all share one fundamental requirement. They all require intense isolation.
Yes, very intense.
A hypervacuum chamber, a deep space freezer, or both. They are completely cut off from the outside world. But what if we want to run a quantum computation in the open air? Or what if we want to send quantum data across the globe? That brings us to the room temperature rebels, photonics and quantum annealing.
This is where we leave the atoms and the electrons completely behind and we start computing with light.
Photonic or optical qubits. The core idea is that we are encoding quantum information in actual individual particles of light, photons. We manipulate them using microscopic beam splitters, interferometers, and optical circuits etched into glass chips.
Which is very different from everything else.
Extremely. But I have a massive conceptual hurdle here. Trying to perform a complex, multi-step calculation on a photon feels to me like trying to write a novel on the side of a speeding bullet.
Yep.
Light never stops moving. It is literally the fastest thing in the universe. How do you hold a photonic qubit still long enough to actually calculate anything with it?
Well, you don't hold it still. You can't. And that is the fundamental paradigm shift of photonic quantum computing. If you try to build a quantum computer with light the same way you build one with matter, you will fail.
So what do they do?
So they use a completely different theoretical framework called measurement-based quantum computing, or MBQC. In every approach we've discussed so far, you take a qubit, you hold it still, you run a logic gate on it, and then you measure it at the very end to get your answer. In MBQC, you do the entire process backward.
Backwards? Wait, how do you measure something before you compute it?
You start by using lasers and special crystals to generate a massive, highly entangled web of photons, millions of them, all linked together quantum mechanically. We call this a cluster state. It is essentially a blank canvas of pure quantum entanglement.
Okay, I have my blank canvas of entangled light. It's flying forward at the speed of light. Now what?
Then you perform the computation by systematically measuring and therefore destroying specific photons in that web as they fly past your detectors.
Measuring destroys them.
Yes. But because they are entangled, measuring one photon instantaneously dictates the state of the others. The sequence of how you measure and destroy them is the logic gate. The computation physically teleports through the remaining unmeasured photons.
Whoa. So my analogy is it's like carving a statue out of a block of marble, but the marble is flying past your head at 1 billion miles an hour, and you are carving it by destroying the pieces you don't want.
That is a remarkably accurate way to visualize it.
But how do you time that?
Right. To handle the insane speed of the light, they use something called time domain multiplexing. In a normal computer, if you need 1 million qubits, you need a massive physical chip with 1 million distinct physical locations. You store data in physical space.
Like rows and columns of memory.
Exactly. But with photonics, they store the data in time. They send photons through long loops of fiber optic cable, delaying them by precise nanoseconds.
Storing data in time. Explain that.
If photon A needs to interact with photon B, but photon B hasn't been generated yet, you just route photon A into a loop of fiber optic cable. It races around in a circle for a few nanoseconds. By the time it exits the loop, photon B is right there waiting for it.
Oh, that's so clever.
They intersect in an optical switch and entangle. You use the dimension of time to shrink the physical footprint of the computer.
That is mind-bending. And the massive commercial advantage here is obvious. Photons don't care about room temperature. They don't interact with ambient heat. You don't need a dilution refrigerator.
Nope.
And crucially, they're naturally compatible with the fiber optic internet infrastructure that currently wires our entire planet.
Exactly. If you want to build a quantum internet, sharing quantum processing power across cities, you have to use light. Matter qubits just can't travel through a cable.
The companies leading this in 2026 are taking massive swings. Look at Sequantum. They are a $7 billion unicorn, and their strategy is borderline insane. While every other company is bragging about 100 or 500 qubits, Sequantum is entirely skipping the small computer phase.
Yeah, they're swinging for the fences.
They aren't trying to build a 100-qubit machine. They partnered with Global Foundries, broke ground on a massive facility in Chicago, and are attempting to leapfrog straight to a 1,000,000-qubit, utility-scale, fault-tolerant system.
It is a massive gamble. The engineering required to deterministically generate identical single photons millions of times a second is staggering. And photon loss, where the particle of light just accidentally leaks out of the waveguide or gets absorbed by a microscopic impurity, is a brutal error to correct.
Because if you lose the photon, you lose the data.
Exactly.
Yeah.
But Sequantum's logic is that small quantum computers are useless anyway, so why bother building them? If they pull off the 1,000,000-qubit system, they win the entire scaling war instantly.
And it's not just the unicorns making promises. Look at ORCA Computing out of the UK. They have deployed their PT2 rack-mountable photonic system at the UK National Quantum Computing Centre. And get this, they are actively using it to optimize fiber network routes for Vodafone.
Right, real-world application.
That isn't a lab experiment. That is real commercial utility happening right now in 2026 on a room temperature quantum machine sitting in a standard server rack.
It proves that you don't need absolute zero to find quantum value, which is a perfect segue into the other technology in this segment, quantum annealing.
Right. Quantum annealing. This is a very specialized approach. I want to be clear for the audience. This is not a universal gate-based quantum computer. You cannot use a quantum annealer to run Shor's algorithm to break internet encryption. You can't use it to simulate complex molecular chemistry.
No, it has a very specific job.
It is designed to do exactly one thing: find the global minimum of a highly complex mathematical function.
It is an optimization engine. And to understand how it works, we need a strong visual. Imagine you are tasked with finding the absolute lowest valley in a massive, rugged mountain range spanning hundreds of miles.
Okay, I've got the mountain range in my head.
If you use a classical computer to solve this problem, it is like sending a hiker out to find the lowest valley. The hiker has to walk up and down every single peak and valley, measuring the depth of each one sequentially. It takes forever.
Yeah, checking one by one.
A universal gate-based quantum computer, on the other hand, is like dropping 1,000 paratroopers across the entire mountain range at once, checking all the valleys simultaneously.
So what does a quantum annealer do?
It doesn't use hikers or paratroopers. A quantum annealer essentially floods the entire mountain range with water and just watches where the water naturally pools. It relies on the principle that physical systems naturally evolve into their lowest possible energy state.
How do you turn a math problem into a mountain range?
You encode your optimization problem, say, the most fuel-efficient routing for 10,000 delivery trucks, or the most efficient way to load cargo onto shipping containers into the magnetic landscape of the superconducting processor.
Okay.
You create a magnetic mountain range, you turn the system on, induce a quantum superposition, and then slowly lower the energy barrier. The qubits naturally settle into the optimal lowest energy configuration. You read that configuration, and that is your answer.
That is wild. You just let the physics solve the math for you.
Exactly.
And the undeniable commercial leader here is D-wave systems. Pure physicists sometimes dismiss them because it isn't universal quantum computing, but D-wave systems are widely used in enterprise right now. Logistics companies, port authorities, traffic routing, they are delivering real business value today by redefining supply chains.
They found their highly specific niche, and they absolutely dominate it.
So what does this all mean? We've covered extreme cold, we've covered lasers juggling atoms, we've covered computing with time-delayed light. But this final segment takes us into the exotics. This is the bleeding edge.
The fun stuff.
Yeah, this is where quantum computing stops looking like standard physics and starts looking like science fiction, advanced chemistry, and biology.
We are entering the realm of the truly profound here.
Let's start with topological qubits.
This is perhaps the most mathematically beautiful approach to building a qubit. Think about every other modality we've discussed. Superconducting, ions, atoms, photons, they all suffer from local noise. A slight temperature bump ruins the circuit. A stray magnetic field wiggles the ion. Their strategy is to accept the noise and try to fix the errors after they happen using massive arrays of error-correcting qubits. Topological qubits aim to be intrinsically fault-tolerant. The hardware itself resists the error at a fundamental physical level.
The technical literature says they use exotic things called Majorana quasi-particles or Majorana zero modes. My analogy for this is normal qubits are like houses of cards. A slight breeze, a tiny thermal fluctuation, and the whole house collapses.
Yep.
A topological qubit is like tying a knot in a piece of string. You can toss that knotted string around, you can drop it on the floor, you can heat it up slightly, and the knot stays perfectly intact. The information is stored globally in the topology of the system, the knot, not in the fragile local state of the string itself.
That is a great visual. I like to think of it as a symphony orchestra. If you were listening to a solo violinist, which represents a standard qubit, and someone in the audience coughs loudly, the performance is ruined. The local noise destroys the signal. But a topological qubit is like the entire symphony playing a grand chord. If one violinist plays a slightly wrong note or someone coughs, the audience still clearly hears and understands the chord. The information is encoded globally across the entire structure.
But let me ask you the elephant in the room question. Is this actually real? Because for years, people have said topological quantum computing is just beautiful theoretical math on a whiteboard. They said these Majorana quasi-particles didn't even physically exist.
It was purely theoretical for nearly 20 years. But look at the 2025 breakthroughs. Microsoft essentially bet their entire quantum division on this math, and they finally unveiled Majorana 1. It is the world's first topological processor.
Wait, really?
Yes. To do it, they couldn't just use standard silicon or aluminum. They had to invent an entirely new class of material, a topoconductor. They grew a semiconductor nanowire made of indium arsenide and coated it with a superconductor made of aluminum.
What does that do?
When you cool that specific hybrid material to near absolute zero and apply a precise magnetic field, it forces the electrons inside the nanowire to do something impossible. They essentially fractionalize.
They split.
Yes, they split into halves, creating these Majorana zero modes at opposite ends of the wire. Because the electron is split, a local disturbance at one end of the wire can't destroy the quantum information because the other half of the information is safely sitting all the way at the other end.
Fractionalized electrons. It sounds like literal magic.
It is incredibly difficult to engineer. Microsoft spent 2 decades and untold billions just to prove it could exist in a controlled lab environment.
But if they can do it.
But if they can reliably produce these nanowires and learn how to braid these Majoranas around each other to perform logic gates, they completely bypass the massive error correction overhead haunting every other company. A topological quantum computer wouldn't need 1 million physical qubits to be useful. It might only need a few thousand, because each qubit is inherently perfect.
So Microsoft is playing an ultimate long game. They are betting that everyone else's surface code error correction is going to eventually hit an insurmountable thermal or engineering wall, and their perfect knotted qubits will just breeze past them.
It is the ultimate high-risk, high-reward strategy in the entire tech sector.
Which perfectly sets up the final piece of our deep dive. Non-conventional chemical and biological qubits. Because if you thought fractionalized electrons were wild, wait until we talk about moving completely away from supercooled metal. The 2026 reports are full of breakthroughs in ambient temperature chemical structures, like diamond and V centers. Let's break that down.
A diamond nitrogen vacancy center is a beautiful defect in nature. You take a perfect diamond crystal lattice, which is just tightly bonded carbon atoms. You remove 2 adjacent carbon atoms. You replace one with a nitrogen atom, and you leave the other spot completely empty, a vacancy.
Okay, so a hole in the diamond.
Right. That specific defect creates a tiny electromagnetic trap that captures a single stray electron.
And you use that single electron spin as your qubit.
Exactly. And because the surrounding diamond lattice is so incredibly rigid and thermally conductive, it protects that trapped electron from thermal noise. It allows the electron to hold its quantum coherence at actual room temperature.
At room temperature. No fridges.
No fridges.
And it goes beyond diamonds. The chemistry literature is buzzing with COFs, covalent organic frameworks. Imagine a microscopic, perfectly geometric honeycomb made entirely of carbon and organic molecules. That's your framework. Researchers have found that they can trap highly reactive organic molecules inside the cells of that honeycomb.
Yeah, the CCOFs.
Right. They've developed chiral covalent organic frameworks, or CCOFs, that achieve phase memory times of 1.7 microseconds at 298 Kelvin.
298 Kelvin is 25 degrees Celsius.
That's 77 degrees Fahrenheit. It's a nice spring day. They're achieving quantum coherence in warm, wet chemical environments.
Which leads to the biological leap, the absolute wildest part of the research landscape right now. Because physicists are starting to realize that to build a room temperature quantum computer, we might not need to invent new chemistry at all. Nature might have already done it.
I am genuinely amazed by this. For decades, physicists stubbornly insisted that quantum effects could only happen in hyper-controlled, isolated, absolute zero environments. The biological environment of a living plant or an animal is warm, messy, fluid, and loud. It should destroy quantum coherence instantly.
It should.
But it doesn't. We are looking at the explosion of a field called quantum biology.
Let's discuss the most famous example, photosynthetic complexes in plants and bacteria. When a photon of sunlight hits a leaf, that tiny packet of energy has to be transported through a dense forest of proteins to the reaction center, where it is converted into chemical energy.
Right, basic biology.
But if that energy transferred classically, just bouncing around randomly from molecule to molecule like a pinball, most of the energy would be lost as waste heat before it ever reached the destination.
But photosynthesis is incredibly efficient.
It operates at near 100% efficiency. Why? Because the energy complex performs the equivalent of a quantum random walk. The energy excitation enters a state of quantum superposition. It essentially explores every possible path to the reaction center simultaneously, maps the most efficient route, and collapses into it.
The plant is doing a quantum computation to eat light.
Yes. And evidence shows that the electronic coherence in these complexes survives for hundreds of femtoseconds at physiological temperatures. The surrounding protein matrix doesn't destroy the quantum state. It has evolved to actively protect and sustain it.
That is incredible. But it gets crazier. The avian compass. How do migratory birds, like the European robin, navigate thousands of miles across the globe? We've known they somehow sense the Earth's magnetic field.
Yeah, but the Earth's magnetic field is incredibly weak.
Exactly. A normal chemical reaction inside a biological body shouldn't be noticeably affected by a magnetic field that weak.
It shouldn't. But inside the bird's retina, there is a specific light-sensitive protein called cryptochrome. When a photon of blue light hits this protein, it knocks an electron out of place, creating what is called a radical pair. Two molecules, each with an unpaired, highly entangled electron.
So the light creates quantum entanglement inside the bird's eyeball.
Exactly. And because those two electrons are entangled, the extreme sensitivity of their shared quantum state acts as a microscopic antenna. It allows them to detect the minute variations in the angle of the Earth's magnetic field. The bird is using sustained quantum entanglement for tens of microseconds to physically see the magnetic field lines.
And then, the final frontier, the brain. There is an emerging, highly controversial theory that human consciousness itself might be rooted in quantum coherence. The theory focuses on microtubules, which are these tiny, hollow structural scaffolds that make up the cytoskeleton inside our neuron.
Right, the Penrose-Hameroff theory.
The theory posits that the brain is essentially a warm, wet quantum computer using subtle isotope effects and protected quantum states inside these tubes to process information in ways that give rise to consciousness.
It is highly speculative, and we must note that many neuroscientists and physicists strongly debate it. But it raises a profound, unavoidable question.
What's that?
If nature evolved molecular architectures that actively exploit noise rather than just tolerating it, what does that mean for our billion-dollar dilution refrigerators? We are spending vast fortunes building the coldest places in the known universe, just trying to hide our delicate qubits from the noise of reality. Nature seems to have found a way to use the messy, warm, noisy environment to sustain coherence.
It is a total paradigm shift. The idea that to build the ultimate supercomputer, we might need to mimic the chemistry of a bird's eye or the scaffolding of a plant's leaf rather than building a colder, more expensive freezer. It's a beautiful thought.
It reminds us that there is always more to learn. We started this deep dive talking about massive industrial machines and global microchip supply chains, and we end up talking about the fundamental building blocks of evolution.
So, to bring it all home, let's distill the key takeaways from everything we've covered in this massive 2026 landscape. First and foremost, the race is no longer about raw, physical qubit numbers. The days of bragging about 1,000 noisy qubits are over. The entire industry has pivoted to the pursuit of logical qubits. Useful, error-corrected qubits. That is the only metric that matters.
Second, there is no single winner. We are in the golden age of competing architectures. Superconducting is the industrial heavy lifter, pushing scale and nanosecond speed. Trapped ions offer pristine, perfect atomic fidelity. Neutral atoms are scaling insanely fast with their optical tweezers and movable arrays. Photonics promises room temperature operation and immediate integration with our global fiber optic internet. Silicon Spin hopes to leverage the massive existing global microchip factories to print qubits, like they print smartphone chips. And topological is the dark horse, betting everything on perfect, mathematically protected knots of quantum information.
Each approach has its absolute genius. Each approach has a critical, potentially fatal engineering bottleneck. The next 5 years will determine which of these physical implementations becomes the foundational hardware of the 21st century.
That's going to be wild to watch.
Which brings me to a final provocative thought for you to take away. For decades, we have built quantum computers by retreating from the universe. We've built extreme vacuums, impenetrable electromagnetic shields, and temperatures colder than deep space. We have desperately tried to isolate our delicate machines from the noise of the environment. But as we just saw with quantum biology, nature went the exact opposite way. Nature evolved to exploit the noise. It uses the messy, warm, chaotic biological environment to somehow sustain its quantum miracles. So as we look to the future of this industry, are our billion-dollar dilution refrigerators fundamentally backward? Will the true, ultimate, fault-tolerant quantum computer of the future be engineered in a sterile factory, or will it be grown?
Think about that.
We'll see you next time on The Deep Dive.